Okay, in this lecture we're going to finish the second part of our section 2.7 material on the cylindrical and spherical coordinate system. And in the first part of this section we had introduced a way to represent points in space. Instead of using the rectangular coordinates x, y, and z, we could use the cylindrical coordinates, which were given by r, theta, z. Where r and theta had similar representations to what we had in the polar coordinate system for points in the plane, and the z-coordinate is equivalent to the z-coordinate from the rectangular system. So in this section, or in this lecture, we will introduce the second coordinate system, the spherical coordinate system for representing points in space. So for this system, a point P in space can be represented by an ordered triple defined as rho, theta, phi, where rho is a non-negative number representing the distance from the origin to the point P. So as we explain these things, let's try to visualize in our figure below here. So we've got a point P shown here in the first octant of space, and this point could be represented either in terms of x, y, and z, or in terms of this ordered triple rho, theta, phi. And here the representation or the interpretation of this first coordinate, rho, is the distance from the origin directly to my point in space. So rho is going to be the distance along that line segment, which by definition is non-negative. Now, theta will be the same angle as in the cylindrical coordinate system. So that is, if I think about the projection of this point P down onto the xy plane, I would have the value x, y, 0. And if I think about in the xy plane, the line segment which connects the origin to this projection, theta is the angle that I rotate by from the positive x-axis in the counterclockwise direction to get to that line segment. So theta has the same interpretation as what we had for the cylindrical coordinate system or for the polar coordinate system for points in the xy plane. And our last value is what we call phi, which is some value between 0 and pi, which represents the angle between the positive z-axis and the line segment connecting the origin to the point P. So here, again, our line segment from the origin to the point P is this line segment. The length of that segment is rho. Phi will be the angle that we have to rotate from the z-axis downward in order to get to that line segment from the origin to point P. And any point in space can be represented in terms of such an ordered triple. So again, if we have a point in space, it might be useful to express it either in terms of rectangular coordinates or spherical coordinates. So we need to come up with a way to convert from one system to the other. So here I'll say if we have a point P whose rectangular coordinates are x, y, z, and its spherical coordinates are rho, theta, phi, then we can define rho. So let me start with these conversion formulas from rectangular to spherical first. So rho is the distance from my point P to the origin. So using the distance formula between 2 points in space, we would have the square root of x squared plus y squared plus z squared as the value for rho. Now since theta has the same representation as in the cylindrical coordinate system. We have tangent of that angle theta is again defined as y over x, the same conversion that we had for points using the cylindrical coordinate system. And the last value would be, how do we find phi? Well, cosine of phi is given by the ratio z over rho. Let's think about y. So if we sketch a little triangle in here. So z would be the vertical distance I traveled along the z direction. This hypotenuse of my triangle is the distance from the origin to P, which is what we've been calling rho. And then phi is this angle measure right here. So if we take cosine of that angle, it would be defined as the ratio of the lengths of the adjacent side, which was z, over the hypotenuse of that triangle, which was rho. So we get this conversion formula. Now using conversion formulas similar to what we had seen for cylindrical coordinates, we could find the rectangular coordinates x, y, and z of a point from its spherical coordinates by using the conversion formulas. X is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. Okay, so using these conversion formulas, let's look at some examples of converting from one system to another. So in this first example, we're asked to find the rectangular coordinates x, y, z of the spherical point whose coordinates are given. So here the coordinates for this point are given in the order rho, theta, phi. So let's find our coordinates x, y, and z. So here x is defined as rho sine of phi cosine theta. So substituting in, well, rho was given as 4. Then we have sine of phi, which was pi over 6, times cosine of theta, which was pi over 4. So let's see what we're left with. We have 4 times sine of pi over 6 is 1/2, and cosine of pi over 4 would be root 2 over 2. So taking this product, we're left with just root 2. Now to find y, we're taking rho sine of phi sine of theta. So rho was given by 4. We have sine of phi, again that was pi over 6, and then times sine of theta, which was pi over 4. So we have a 4 times sine of pi over 6, which is again 1/2, times sine of pi over 4, which is root 2 over 2. So our y coordinate is also root 2. And then our z coordinate is determined by rho cosine of phi. Now rho was equal to 4. And then we're multiplying by cosine of phi, which was pi over 6. So we get 4 times cosine of pi over 6 is root 3 over 2. So taking this product, we've got 2 root 3. So our point P could be given by the rectangular coordinates x, y, z, which is given by root 2, and 2 times root 3. Okay, Now let's look at an example moving in the opposite direction. So here we're asked to find the spherical coordinates, rho, theta, phi, of the rectangular point given by x, y, z is equal to 1, -1, -2. So we'll start by looking for rho. Rho is defined as the square root of the sum of x, y, and z squared. So substituting in our rectangular coordinates, we would have the square root of 1 squared plus -1 squared plus -√2 squared would be 2. So we're left with rho is √4 or 2. Now to find theta, we would make use of the fact that tangent of theta is given by y over x. So here tangent of theta would be -1 divided by +1, so just -1 there. So we're looking for the angle theta such that tangent of theta would be -1. So we would have the angle measures 3 pi over 4 or 7 pi over 4. And the question is, well, which angle do we want here? So we need to think about which quadrant this point lies in if we project onto the xy plane. And we can see from our point that x was positive, y was negative. So we're looking for a point in the fourth quadrant of our xy plane, which would correspond to the angle 7 pi over 4. And to find phi, we can make use of the fact that cosine of phi is equal to the ratio, let's see, what was it, rho over z or z over rho? So here we would have cosine of phi is z, which is -√2, over rho, which we calculated in the first part of the problem as 2. So cosine of phi would be -√2 over 2, or -1 over √2. So the angle phi that would produce a triangle such that cosine of that angle measure is -1 over √2 would be 3 pi over 4. Recall here, so there's another angle possible, but recall that phi here must lie between 0 and pi as part of our definition. So another such angle would be 5 pi over 4. However, since phi must lie between 0 and pi, we would take only this first angle measure. So our point could be represented as the point rho theta phi given by 2, 7 pi over 4, and 3 pi over 4. All right. So next we'll consider equations involving either rectangular or spherical coordinates and think about the surfaces they represent. Now certain surfaces have very simple representations in terms of spherical coordinates, which we'll see here. So we're asked to describe the surface with the given spherical equations. And in part A, we have a constant value for rho. So let's think about this. We can either intuitively see what sort of surface this describes, or if we convert to rectangular coordinates, we know that rho is defined as the square root of x squared plus y squared plus z squared. So if that's equal to 7, Then squaring both sides of this equation would give us x squared plus y squared plus z squared is 49. And we can recognize this equation as the standard form for the equation of a sphere centered at the origin of radius 7. Now we might have immediately seen that from thinking about the interpretation of this equation. So recall rho represents the distance from the origin to our point. So if that distance is a constant value, 7, we're looking at the set of all points in space that are 7 units exactly from the origin, which would be points on a sphere of radius 7. So either approach we use there, an intuitive idea or this conversion, we see that our surface is a sphere centered at the origin of radius 7. So a constant value of rho means that we're discussing or an equation which is a constant value of rho is describing a sphere of constant radius, or a sphere whose radius is given by the constant value of rho. So let's look at another example. Suppose we have a constant value of phi. Say phi is equal to pi over 4. So we can think about this one perhaps intuitively, where let's see, I think the easiest way to think about this is intuitively rather than looking at the conversion. The conversion working backwards is a little tricky. So here a constant value of phi being equal to pi over 4 means that we're looking at the set of all points in space which were obtained by rotating downward from the positive z-axis by an angle of pi over 4. So here we would be describing a cone, in particular the upper half of a cone, at an angle of phi equals pi over 4 radians, or 45 degrees, from the z-axis. So here would be a description. Now to sort of visualize that, let's think about why this makes sense. If we have our x, y, z space, if we're looking at the set of all points which are rotated downward from the z-axis by an angle of 45 degrees, we would be describing a cone where this angle of rotation from the z-axis is our constant value of phi. In this case, pi over 4 radians, or 45 degrees. So let's consider that a constant value of phi could represent a cone angled at a particular angle measured downward from the z-axis. Now, if we happen to have the particular constant, let's say phi is equal to pi over 2, that means that we've rotated 90 degrees downward from the from the z-axis. So that particular case would be describing the xy plane itself rather than a cone. Now in our last part, part C, we have rho is equal to 4 sine phi cosine theta. So as it's written, it's difficult to see what sort of surface that might represent. So let's see if we could make use of our conversion formulas. Now, when I look at the right-hand side of this equation, I have something of the form 4 sine phi cosine theta. And when I think about my conversion formulas, well, I know that x is equal to rho sine phi cosine theta. So that's almost what I have on this right-hand side. I'm just missing the rho out in front. So let me start here by multiplying both sides of my equation by rho. So I would have rho squared is equal to 4 rho sine phi cosine theta. And now converting to rectangular coordinates, well, rho squared would be the sum of x squared, y squared, and z squared. And that is equal to 4 times rho sine phi cosine theta is exactly x in terms of rectangular coordinates. Now, this sort of equation, I claim, represents a sphere. This is similar to some of the problems that we looked at the beginning of chapter 2. In order to see that this represents a sphere, or to find its center and radius, I could group all of the variables on one side of my equation and collect the x, y, and z terms respectively. So I will subtract 4x from both sides, and then I collect all my x terms together. And for this quadratic involving x, if I complete the square by adding 4, and the y and z quadratics are already perfect squares, then I would have the following equation. So again, by adding 4 on that left-hand side, I must also add 4 on the right-hand side of my equation to keep it valid. And I can now factor this x quadratic as x minus 2 quantity squared plus y squared plus z squared is 2 squared. So this would represent a sphere centered at the point 2, 0, 0 with radius 2. Okay. So to see what sort of surface is described by an equation in terms of spherical coordinates, we can either convert to rectangular coordinates, or as we did in maybe parts A and B, think about what that represents intuitively to describe our surface of interest. So for our last example, let's consider some problems working in the opposite direction. So here we're given equations in terms of rectangular coordinates. We're supposed to describe the surface represented by these equations and then express these equations in terms of spherical coordinates instead of rectangular. So these were similar, or these are the exact same equations that we had in the example in the earlier part of this lecture, or this section where we were looking at cylindrical coordinates. So looking at part A, we have x squared plus y squared plus z squared is 36, which represents a sphere centered at the origin of radius 6. So here is our description of that surface. And we're supposed to then convert this to an equation in terms of spherical coordinates. So a couple of ways we could do it. Formally, when we look at the sum of x squared plus y squared plus z squared on this left-hand side, we can recognize that as being rho squared, since rho was the square root of the sum of those squares. And this has to equal 36. So it follows that rho must be equal to 6. So as we saw in the previous example, a constant value of rho describes a sphere centered at the origin whose radius is given by that constant value of rho. So really, instead of using this formal conversion, once we know that we're talking about a sphere centered at the origin of radius 6, we could immediately jump to this equation describing that sphere. So of course the equation for a sphere in terms of spherical coordinates is much simpler than its equation in terms of rectangular coordinates. Now in part B, we had the equation z is 12 minus 4x squared minus 4y squared. So this is a elliptical or an elliptic paraboloid along the z axis. Has its vertex at 0, 0, 12. It's opening downward, sort of like we saw in our earlier example from this section. So let's see if we can convert this to an equation in terms of spherical coordinates. So here, let's take a look at this. We have z is equal to 12 minus, if I factor out a 4 from these second two terms, I've got x squared plus y squared. Now let's think about what z is equal to in terms of spherical coordinates. Z was given by rho cosine phi. That's equal to 12 minus 4 times, okay, let's look at x squared plus y squared. So x in terms of spherical coordinates is given by rho sine phi cosine theta, but we were squaring x, so that would give us rho squared sine squared theta, or sine squared phi cosine squared theta, and then plus y squared. Well, y is equal to rho sine phi sine theta, but since we were squaring y, we would have rho squared sine phi squared sine theta squared. So let's take a look at what we've got here. We've got a rho cosine phi is equal to 12 minus 4 times, well, let's look at what we can factor out. We can factor out a rho squared times sine squared phi from each of these terms. And we are then left with the sum of cosine squared theta and sine squared theta, but the sum of sine and cosine squared of the same angle is 1. So what we have is rho cosine phi is equal to 12 minus 4 rho squared sine squared phi. Or if we care to rewrite this just a little bit, we might rewrite this so that all of our variables are, say, on one side. We would have rho cosine phi plus 4 rho squared sine squared phi is equal to 12. So this example in part B illustrates that using spherical coordinates for some surfaces would not be very beneficial. The equation for this paraboloid in terms of the rectangular coordinates, x, y, and z, is much simpler than the equation that we obtained in terms of spherical coordinates. Now in our last example, part C, we have z is the square root of 3x squared plus 3y squared. So under that radical, if we factor out a 3, we're left with x squared plus y squared. And taking the square root of each term, we would have root 3 times the square root of x squared plus y squared. So let's see what we are left with. What surface this describes. So we can recognize this as the equation of a cone, in particular the upper half cone. So let me specify. We would have the upper half cone along the z-axis. So let's see if we could describe this using spherical coordinates instead of rectangular. So using our conversion formulas, well, we know that z, the left-hand side of our equation, is equal to rho cosine of phi. That's equal to, on our right-hand side, we had a root 3 times the square root of x squared plus y squared. Now, using some of our earlier work to simplify here, x squared plus y squared, in the previous part, part B, we saw simplified down to rho squared sine squared phi. So rather than going through all those steps of simplification again, our x squared plus y squared is equivalent to rho squared times sine of phi squared. So taking the square root of that expression, I'm left with rho sine of phi. And I see here that I can cancel a factor of phi on both sides. So I'm left with cosine of phi is equal to root 3 sine of phi. Or if I simplify this a little bit, say if I divide through by cosine theta, or cosine of phi, I have 1 is equal to root 3 times sine phi over cosine phi. Or if I divide both sides by root 3, 1 over the square root of 3 is equal to sine over cosine of phi, which is tangent of phi. So let's see if we can solve for phi. Phi would be the angle by which I rotate to get a triangle or a value of tangent of that angle that would be given by 1 over root 3. So let's see, we can find it using a reference triangle. Our opposite side has to have length 1, our adjacent side length root 3, which means that we're looking at the angle pi over 6 radians. So this would be the equation for that cone given in terms of spherical coordinates. It's a constant value of phi. Same as what we saw in that previous example where a constant value of phi represented a cone. So here we see that for spheres or for cones or portions of cones, we can easily represent these things by using spherical coordinates because we have just a constant value of rho or a constant value of phi. And this is something that will be very useful later in our course when we start talking about integrating functions in 3 dimensions or integrating vector functions in 3D.